Welcome all my dear student of FYBSc class. In previous lecture we studied the definition of elasticity, units and dimension of elasticity, stress, different type of stresses, strain, different type of strain, then unit and dimension of all type of strain and stress, and we also studied the modulus, one modulus of elasticity, that is Young's modulus, in detail. Now in this lecture we are going to see two remaining modulus. One of them is bulk modulus. Notation for this is small k, and another is the modulus of rigidity, and notation for this modulus of rigidity is eta. Okay. Now first of all we are going to see the bulk modulus. Like Young's modulus, this is also a ratio, and hence by the similar way we can define bulk modulus in a single sentence. And see here the definition of bulk modulus, very simple. Bulk modulus is defined as the ratio of volume stress to volume strain. Okay. Bulk modulus, that is K, is defined as it is the ratio of volume stress to volume strain. Okay. When deforming force is applied normally, that is perpendicularly, suppose this is a body, and on this body if we apply the force normally, that is perpendicular to face, any face, or perpendicular to the surface of the body, its volume changes. Okay, its volume changes. Suppose original volume is V and change in volume is small v. Applied force is F and area of surface is A. Then change in volume per unit volume is nothing but volume strain, and applied force per unit area is nothing but volume stress, and therefore volume stress is nothing but F upon A, and applied volume strain is nothing but small v upon capital V, or from this we can write F V upon what A V, but F upon E, we know that pressure, force is equal to what? Force is equal to pressure into area, or pressure is equal to what? Force upon area. Then instead of this we can substitute P, therefore P V upon small v is nothing but bulk modulus K. Okay. Now unit and dimension of bulk modulus is same as that of pressure. Okay. What is the dimension of pressure? M raised to 1, L raised to minus 1 and T raised to minus 2. And unit of pressure is nothing but again Newton per meter square, SI unit, and dynes per centimeter square is CS unit. Okay. Remember that 1 upon K is nothing but compressibility, and hence we can say that the reciprocal of bulk modulus is called compressibility. Now the last modulus, that is modulus of rigidity, last one. And this is denoted by eta. Again this is also a simple modulus, or we can define very simple way. Again it is the ratio of Modulus of rigidity is the ratio of shearing stress upon shearing strain. Most of the time shearing strain is simply called as shear, and hence shearing strain or tensile strain, shearing strain or tensile strain upon shear. In this way we can define the modulus of rigidity. In order to understand this, then we are going to consider a cube. Suppose this is a cube. A, B, C, D is the front face, and E, F, G, H. Hence this is the cube. A, B, C, D, E, F, G, H is the cube. Okay. The surface, that is CD, GH, that's this surface is fixed. This surface CD, GH or CDHG is fixed, and the tangential force F, this is the tangential force, is applied on the surface ABEF. This is the upper face and this is the lower face. Lower face is fixed, and we apply the tangential force on the upper face ABEF. What happens? Deformation takes place. This point A is shifted to this point A prime. This E point is shifted to E prime. F point is shifted to F prime, and B point is shifted to B prime. And in this way we get the deformed structure. The red dotted line shows the deformed structure. Suppose this is the length, change in length. This is the length L. Okay. And small change, that is the change in length. This is L. And this is the angle of deformation. Same here, every point. Okay. Now see here. This surface is fixed and upper surface is displaced. But what will be the twin observation? It is found that as the lower surface is fixed, then surface, or we imagine that this cube is made up of number of layers. The layer which is very close to the face CDGH, it is less displaced, whereas the layer ABEF is displaced widely, or large displacement is found here. That means what? As we move towards the length, if length from the base fixed surface goes on increasing, then displacement of the layers or layer is also goes on increasing, and therefore we can define strain. What is shearing strain? Shearing strain, or simply shear, is equal to what? Displacement of the plane. Of the plane to the distance of plane. Suppose displacement A prime. This is A prime is the displacement A prime, and change in length is length is AD. AD means, suppose here we can write AD AD is the length. Therefore here we can write, and this is nothing but tan theta. As theta is very small, then simply tan theta is approximately equal to theta, and therefore shearing strain or shear is simply theta. Okay, and what is the applied force? F. What is the area of the face? Is A. Therefore force per unit area is shearing stress, and shearing stress is theta. Or here from this we can write F upon A theta, or F upon A is the tangential force. From this we can write T upon theta. This is nothing but modulus of rigidity. Okay, again here the unit and dimension of modulus of rigidity is same as that of pressure, that is m raised to 1, L raised to minus 1 and T raised to minus 2. Okay. Now this modulus of rigidity, like Young's modulus, only solid possesses modulus of rigidity, and liquid and gases does not possesses modulus of rigidity because they do not have their own shape. Okay, and hence from all three, Young's modulus, bulk modulus and modulus of rigidity, it is found that only solid possesses all the three elastic modulus y, k and eta, while liquid and gases possesses only elastic constant, that is bulk modulus. Okay. Now the next point is work done during longitudinal strain, volume strain and shearing strain. Next point. There are three derivations, and these derivations are very important for exam point of view. Work done during longitudinal strain, then volume strain, and last shearing strain. Now in this lecture we are going to see the work done during longitudinal strain. Okay, just a minute. Okay, now consider a wire. One end of the wire is fixed to rigid support, and at the free end the stretching force is applied. Suppose L is the length of the wire and small n, or say x, is the change in length. Okay. What happens when the stretching force is applied? Sorry, here only this is the length force. Now what happens when we stretch the wire? Stretch the wire, the deformation of wire takes place. That is, the length of the wire is increased by the quantity x. This is the original length. Here the force is Ay upon L into x. See here, the force is so adjusted, very important one. What I say, very important one. The force is so adjusted that the wire is slowly stretched. Don't apply vast or large force. the force is so adjusted that the wire is slowly stretched. Therefore, at any time during the extension, the external force is equal to the tension in the wire. Means what? External force and internal restoring force or internal resistive force should be same at any moment, at any time. When the extension of the wire is x, the wire is undergoing a longitudinal force F upon A. This is the longitudinal force, and longitudinal strain in the wire is nothing but x upon L, and therefore Young's modulus is nothing but F upon A upon small x upon capital A. This is nothing but according to definition of longitudinal stress upon longitudinal strain. Okay. Okay, from this point we can define force equal to, what is the force? Ay upon L into x. Suppose this is equation 1, this is equation 2. The work done by the external force in further extension dx will be dw is equal to f dx. Suppose this is equation 3, but what? F is nothing but this. Therefore, dw is equal to a y upon L into x dx. This is the small work done during infinitesimal change. Now, we are going to calculate the total work done by the external force in the extension from 0 to L. And this will be obtained by integrating this equation between the limit 0 to L ay upon L x dx or ay L x. When you solve this, you will get 2L 0 to L. Okay, this is nothing but 1/2 ay into L into L square. Okay, this is the work done. This is the work done stored in the wire as elastic potential energy. What I say? This work done dw is stored into wire as elastic potential energy. Elastic potential energy. Thus, elastic potential energy of the stretched wire is nothing but U, because same work done is stored into the wire in the form of elastic potential energy. This is nothing but elastic potential energy. Or from this we can write U is equal to 1/2 A y upon L. See here, there is a little bit arrangement into L into L. Sorry, this is capital L and this one is L. See here, only we split this L into L into L. L square is nothing but L into L. What is this? This is the stretching force and this is the extension. This is extension, this is stretching force. And therefore, from this we can say that potential elastic potential energy is nothing but it is equal to 1/2 stretching force into extension. Okay, suppose this is equation 5 and this is equation 6. Now from equation 5 we can also write, from equation 5 or equation 5, this equation 5 can be expressed here. U is equal to 1 half, sorry, into bracket y small l upon capital L, in another bracket L by L into C remaining quantity AL. This is the splitting of this equation. Okay. And hence work done per unit volume of the wire or strain energy per unit volume of the wire is nothing but U upon AL. This factor is come here. Take here, and 1 half simply Y L upon capital L into small l upon capital L. This is nothing but 1 half stress into strain. Okay, and hence work done during longitudinal strain is nothing but 1 half stress into strain, but strain is longitudinal strain and stress is longitudinal stress. Okay. Now in the next lecture we will see the work done during volume strain and work done during shearing strain. Remember that in every strain the final result will be one and the same, that is during every strain, that means longitudinal strain, during volume strain, during shearing strain, the final result will be work done during every strain is nothing but 1 half stress into strain. Okay. Hence question may be asked that like that. Show that work done during, suppose first work done, show that obtain an expression for work done during longitudinal strain. Second question, obtain an work done for volume strain. Third one is obtain an expression for shearing strain, or show that during every strain work done is equal to 1 half stress into strain. Okay. I told you that in the next lecture the remaining 2 points, that is work done during volume strain and work done during shearing strain, will be studied. Till then we shall stop here. Have a good day.